Okay. All right. So yeah, thanks for giving us the opportunity to present. So it was actually very interesting to participate in the challenge, because one of the things we always struggle with is finding like good benchmark problems to evaluate these systems on. So I think this is a great initiative, and I hope to see it expand in the future. All right, so let me dive right in. So the system we built is, we call it CountCP, because it comes from it's an extension of a system we built earlier, CountOR, for scheduling problems. And this is work with Mohit Kumar and Tias Huns. Mohit made slides, so thanks for that, Mohit. All right, so there's kind of like a general theme in which constraints are learned through kind of generate and test methods. So you like have a bias, like a set of primitive constraints and maybe rules to nest them. And then you try to generate a constraint, and then you basically test, like, okay, does the constraint hold or not? And the constraint is basically like a primitive that is either holds or it doesn't hold. Now, we've had experience with a system called CountOR, where basically instead of having this kind of set of primitive constraints, we instead learn bounds over expressions. And then when we learn the constraints, what we're doing is we take examples and turn them into tensors, and then constraints are this aggregation of these bounds. So what does this mean? So for example, if you have like a nurse scheduling problem, or you have like some nurses, different days that they work on and different shifts per day, you get like a tensor of decision variables, like let's say tell you whether or not the nurse works. And then you learn an expression. In this case, it's like nested summations and slices of the tensor, and then taking the max and min to get like these bounds. And then you get something like the number of working days has to be smaller or equal to 3. So that's the kind of constraints that we learn in that case. And this was kind of an interesting approach, because this takes away this usual approach where you just say, okay, yes or no, there's a constraint. Instead, we're looking at the quantities, like these bounds. And that's led us to what we considered for this submission, CountCP, where we learn a bound over mathematical expressions, just like in CountOR. So we have a lower bound, an expression, and upper bound. And we use a grammar to decide what kind of expressions we're testing for. So the flow of the system kind of goes to get the data tensor in, we have our language bias, and then we learn these kind of expressions, these kind of bounded expressions. And those are the constraints. So let me make this a bit more concrete. So if we have these example lists, so we have 3 decision variables, x1 to x3. We have 3 solutions and instantiations of those decision variables. We turn that into matrix here. We have our language binary bias, some unary and binary operators. And then at the output, we'll get constraints such as the absolute value of the difference between x0 and x1 is between 1 and 4. And we represent this as this kind of tuple where we have the expression, then the indices of the variables that are involved in that expression, and then the bounds, the lower and the upper bound. Now, the grammar we used here, we looked at only binary and unary expressions. And I'll say a bit more about that in a second. So for the unary expressions, we considered just the identity and absolute value for now. And the binary expressions are then made up of unary expressions, which are either summed, or we take the difference, and then we have 2 ways to take the difference, x minus y or y minus x. And then we can wrap that again into another expression. Now, this is a very limited set, but it already captures a lot of powerful constraints. And obviously, you could extend it with a modulo 2 or power in the future, and it would just work the same. And so, yeah, the type of expressions we can learn is x minus y, absolute value of x minus absolute value of y if there were negative values involved. But we don't have specific constraints such as x minus 1 is not equal to x2, but we do capture these kind of things because that can just be rewritten as the absolute value of x1 minus x2 is larger or equal to 1. So in that case, we'll always get the difference. So like a lot of interesting constraints can actually be rewritten as bounds on these type of expressions. And we also don't have global constraints, at least not in this first stage. But any global constraint can be decomposed into binary constraints. So we just get a not equals, and then we get a bunch of binary constraints that say not equals. So let's look at the easiest setting where we have solutions of the same size, and we're trying to learn over those. So just Sudokus of size 4 in this case, or size 9. And so there's 4 steps: generating and computing the expression bounds, translating them to constraints, removing implied constraints, and then dealing with the objective function. So if we have these, every row here is an example, and then every column is a decision variable. But basically we do is we generate all expressions, and we're taking really like a brute force approach here. We take all possible expressions over all unary variables and all pairs and compute their value. So for each example, what's the value of that expression? And then we just go and aggregate over the columns to find the minimum and maximum value for that expression. So here, for example, x1 plus x2 is between 1 and 8. So it's that easy. In the next step, we just take these constraints, we translate them to CP_MPy constraints. So CP_MPy is like a package where you can easily model the solver agnostic constraints. Then they're solved using OR tools or Minizinc in the background. And so we encode the constraints, and then we remove implied constraints. So we can already look at trivially implied constraints, so or an unnecessary constraints, if the sum of 2 variables is just the sum of the minimal domain elements of those variables, then this constraint doesn't really help, right? So we can look at the lower bound and maximal bound, and if they're trivially true, then we just remove those bounds. But for a bit more involved constraints, what we do is we greedily check whether constraints are implied by other constraints. So we take all of the constraints, and then we take one out, and we check whether the set of leftover constraints implies the extra constraint. And what does this mean? It just means whether there is a solution for C1 and not C2. So you can just feed this, CP_MPy will give you the answers. And obviously there's a bit of an ordering question here. So what we looked at, we tried to first add less complex constraints, and where the complexity is defined by like the grammar. Basically, if you have to generate, go through more steps than you want to, then that constraint is more complex. And so you want to add it later, so that in case that there's 2 equivalent constraints, the simpler ones are kept. Obviously, there's a lot of room to do something more fancy here. Yeah, so we prune the constraints that are implied by other constraints, and we get smaller model, not necessarily minimal, because there can be groups of constraints that imply each other. For the objective function, for this challenge, we didn't do a whole lot about it. So it basically mostly involves like expressions like min, max, or average over the decision variables. And for type 3, actually, we manually hard-coded this weighted sum. We see this kind of as more a bit like equation discovery. We didn't really have the time to work it out completely, but I think also in case like if you're dealing with nurse scheduling problems, there might be some kind of fairness objective function, etc. So I think we think that like an equation discovery approach would be the way to go here. Okay, all right. So this approach worked pretty well. So if we're just looking at instances where we try to solve the same size problems, we actually find a lot of the constraints. By construction, they satisfy the positives because we just take the bounds. In a 2D representation, you can kind of imagine it as a convex hull. And we found that, okay, in most cases, you actually exclude most of the negatives. We didn't explicitly use the negatives while learning, but obviously, again, they are useful when you're, I mean, Helmut already said everything about this basically in the slides. But yeah, when you're looking at the constraints and just constraints that don't exclude any negative, then you could say, okay, I might want to exclude this one. Now, obviously, the problem is that if you learn these constraints, as I said, like you can learn an all difference, it's not a problem, but it's not an all difference in the sense that if you scale the problem, you're not automatically getting the right indices. You basically hard-coded the all difference. And so we tried to look for a solution to this, where we wanted to have a similar approach where we can say, okay, we don't want to necessarily hard code all the constraints that could occur. We want to have a flexible grammar that you can just edit. And we still want to find some kind of generalizable constraints. So what we did here was to say, okay, we're going to group index sets of identical expressions. Basically, we find sets of indices for which a similar constraint applies. And so let me give an example. If you have different expressions here, like x1 minus x, so it's the same expression, but over different tuples of variables, you basically group them and you say, okay, if I aggregate them over all of the pairs, for example, then I get a generalized constraint. So the constraint absolute value of xi minus xj. And then instead of having two hard-coded indices, we have a generator expression for each pair. But it could also be for each like sequential pair, or for all even pairs, or for all odd single unary variables. And then we look at the bounds, and we compute it by aggregating over the bounds of the single tuples that we have on the left side. And then we can also do this again by looking at the different instance sizes and again aggregating those. So you do this for the Sudoku of size 4, you do this for the Sudoku of size 9, and then you aggregate those again to get the expressions that can scale to Sudoku of size 16 or 32. Okay, so here again we have a grammar for these index set generators. For unary, we considered all of them even and odd numbers, and for binary, we have something similar, but we also have the sequence, so that we're looking for constraints between x1 and x2, x2 and x3, x3 and x4. And so this constraint must hold between all of these. Yeah, I'll come back. There's a shortcoming here, but I'll come back to it in the future work section. So again, this satisfies all the positives, but if you take this alone, we are not as expressive anymore. So we do cover more negatives. So this approach does allow us to generalize, but we give something up, because now we don't have all the individual constraints. Instead, we look for groups that have the same constraint, but so we lose some of the expressivity. If, for example, there is an all difference over just subsets of the decision variables. This is a problem that we weren't able to address yet on time for the challenge. But the models can be used to learn to generate to solve problems of different sizes and generate new solutions. So yeah, we have to conclude, what we did was we used a grammar of expressions and bounds on tensors. That's kind of the core idea behind our approach. And we kind of found that just having unary and binary expressions provides a rich enough bias to learn a lot of constraints. By using generator expressions, this is definitely an interesting proof of concept that you can generalize across different instance sizes. And we were able to use CP-MPy as an environment for constraint learning, because we can quickly express the learning algorithm and then solving them to find new solutions or to evaluate redundant constraints. Now, I think there's a few key things to make this really work, which we would have to invest more time in. I think to have grammars over multiple tensors of variables. So right now, we did allow for multiple input tensors, but we basically put them to solve constraint learning problems for them separately. So we didn't really have the crossover between the tensors. And this is obviously something that needs to be addressed. The input data would also need to be integrated in the grammar. We only did this in a very limited sense, but this is something that you need to take into account. So the input data kind of gives you inputs for what you should generate for your grammar. When you're looking for generalized problems, there's two big things that need to be done to make this really work. One is to drop the approach that we have with constants. So if you don't want to say the size needs to be below, like the sum of two variables needs to be below 4, no, this 4 might actually depend on the problem size. So instead, you want to generate here bounds that are symbolic. So the length of a variable, the length of a dimension of a variable, a specific constant of the input data. So basically, you have to substitute these constants with symbolic variables that are provided as part of your input. And secondly, when you're trying to generalize expressions, having the generator group is great, but you also need to consider subsequences of tensors. I think this is also one of the core things that really make Model Seeker shine, where you consider how am I going to partition my tensor such that I then can learn constraints that hold over every partition. And so I think finding these partitions is something that we considered, but we didn't have time to finish it. But I think that would really make it complete. All right, thanks very much for your attention. Thanks for setting up the challenge. It was a lot of fun to work on.